Hi everyone, in this video I'll be going over section 3.5. The segment of it is about the derivatives of inverse trig functions. So the reason this is built in with implicit differentiation is because commonly to figure out what the derivatives of the sine inverse, the cosine inverse, the tangent inverse, etc. functions are, we use implicit differentiation. So I'm going to go ahead and go through the reasoning behind the derivative for sine inverse, and then I'll give you the rest of them with the notion that if you wanted to actually prove why it's true, you would go through a very similar process. So we won't prove all of them, I'll just prove one. Usually in class I have students prove the remainders as an activity together, but for time's sake, I won't have you do that. So before I get started, I did want to mention a couple of things about the sine inverse function, and this is mostly related to prereqs, but the first thing is this can be named in a couple of different ways. So the text kind of flip-flops back and forth between them. I think this happens when you're in prereq classes too. Oopsie, so keep in mind that, oh boy, there we go, okay. When we have the sine inverse of x, all right, we can also call that the arc sine of x. So some people use sine inverse, some people use arc sine. Similarly, you could say cosine inverse or arc cosine. That means the same thing. I will use sine inverse, cosine inverse, tangent inverse, etc. This text kind of flips back and forth between the two. So that's one thing to keep in mind. The second thing to keep in mind is the sine inverse function is the inverse of the sine function. All right, inverse and reciprocal are not the same thing. So whatever you do, do not do this. Okay, so sine inverse of x is not the same thing as 1 over sine of x. So a lot of times students will see that sine inverse and say, oh yeah, okay, so 1 over sine. Well, no, 1 over sine is the cosecant. It's not sine inverse. So the inverse of sine, okay, really undoes the sine. All right, and I'm going to talk about this in a minute. Okay, so they're inverses of one another, not reciprocals of one another. So the reciprocal of sine is 1 over sine. That's cosecant. The inverse of sine is denoted sine inverse or arc sine. So keep in mind, inverse, reciprocal with trig functions, not the same thing. So try to be aware of that. Okay. So now that we've talked about that, let's go ahead and look at the derivative of the sine inverse function and the reasoning behind that. You will have to have a little bit of prereq knowledge, though I'll try to spell some of it out for you. And I do think it's important to understand this. The reason for that being, when you go to Calc 2, you essentially have to undo derivatives. So in Calc 2, you kind of do the opposite of take derivatives. You start with a derivative function and then try to get back to an original with something called an antiderivative. So with the trig functions, I find that when I teach that class, the integration, aka the antiderivative method of for inverse functions, is the most difficult for students, and that's because they don't totally understand the reasoning, and then it's a little bit harder to see it. So I do think this reasoning is important. I emphasize it a lot, when I teach this class in person. So I'm telling you right now, you should pay attention to this proof and have some desire to know why this is true and what's going on with it. So anyway, let's start with the function f of x is equivalent to, that's not a very nice looking s, the sine inverse of x. Okay, so if I started this and I said, all right, find the derivative, you, if we were in class, would say, well, I don't know the derivative of sine inverse, so I can't just find it right now. And I would ask you, okay, well, why is it difficult? What's causing the problem? And you would probably tell me, well, the inverse thing. I don't know what the derivative of the sine inverse is. So if the sine inverse weren't there, it wouldn't be so difficult. So what we're going to do is undo the sine inverse function. The only way to undo an inverse function is with its own inverse. So if I take the sine of both sides, that would be the sine of f of x equals the sine of the sine inverse of x. All right, here the sine undoes the sine inverse because they're inverses of one another. So what I'm really left with is the sine of f of x is equivalent to x. All right, so at this point, I need to go ahead and take derivative of both sides because in the end, I'm trying to find the derivative. I want f prime of x, so let's take the derivative of both sides using either prime notation or derivative notation. I'll just use prime notation for now. So I take the derivative of both sides, derivative. When I do so, the derivative of sine, so I'm gonna have to use the chain rule, I'll spell that out too. The chain rule on this, so my big function is the sine of x, and my little inside function is f of x. So when I use the chain rule on this, the derivative of the outside is the cosine. I have to fill the inside back in, so fill the f of x back in there. Okay, and then I need to multiply that by the derivative of the inside, so times f prime of x. Okay, and then on the right-hand side of the equivalent sign, we have equals, the derivative of x is just 1. All right, so looking at this, I'm thinking, okay, this is a good thing. I have that f prime in there. I know I really want to find the derivative of f, the derivative of this function, so that's awesome. Now I want to isolate that though. So I'm going to divide the cosine of f of x over to the other side. Whoopsie. Here we go. So when I do that, I have f prime of x is equivalent to 1 over the cosine of f of x. All right, well now we have this f of x in here, and it'd be a little weird, like, you know, I actually wanted you to take the derivative to have to write this out, plug whatever your original function was back in there, and then simplify it and make it nice to work with. So we want this to be all in terms of x. We don't want the second function in there. That means I'm gonna have to figure out how to replace it. So what we have to remember is what the original f of x was equal to. So let's note that. So note that f of x is equivalent to, was equivalent to, the sine inverse of x. All right, so after noting this, we have to realize, well, what is the sine inverse? So if I go ahead and plug this back in, so I'm just plugging f of x back in, I'd have f prime of x is equivalent to 1 over the cosine of the sine inverse of x. So this would mean if you actually took the derivative and used this, you'd have to go and back plug things in and then figure out what your x value was, and then what the sine inverse of that was, and then what the cosine of that is, which would basically mean you'd be doing a ton of trigonometry when maybe there's something more efficient. So we want to break this down even more. In order to do that, we need to recognize what an inverse produces. So when you take trig, you find that when you take the inverse of the value, it really produces some angle. So I'm going to call that angle theta. All right, so now what we're looking at, I'll just write this out. So focus point, and that's that we're calling theta, the sine inverse of x. And that's because the sine inverse of x produces some angle measure, and theta is a common way to express an angle. All right, well, what this means is, let's see how much room I have here. I'll write this up here. Okay, put this up here. So if theta is equivalent to sine inverse of x, if I take the sine of both sides, I would see that the sine of theta is equivalent to x. So here I have the sine of theta on the left. The sine undid the sine inverse, which left the x on the right. All right, so now if I can use this concept, the knowledge that the sine of theta is equal to x, to somehow replace this cosine of theta that was in the denominator of this fraction, I can make it so I have something that's a little bit nicer to work with. So what I'm going to do is use this information to draw a triangle, right? So first thing to know is that x is really the same thing as x divided by 1. They're equivalent. All right, now I'm going to create a triangle. So what I'm going to do is draw a triangle with some knowledge from my right triangle trig. So remember, sine, cosine, tangent are all involved in right triangle trigonometry, so they go with a right triangle. So with sine, and this goes back to the prereq stuff I talked about, I think it was at the beginning of the 3.3 notes, sine is equivalent to the opposite of the triangle over the hypotenuse of the triangle. So if I draw a triangle out, all right, I have my theta angle measure. The opposite is x. The hypotenuse is 1. All right, if I wanted to try to find the cosine, right, this whole thing is the cosine of theta, so I'm looking for the cosine of this triangle, then I'm going to need this bottom value right here. Well, we have a right triangle with two sides, and that means we can use the Pythagorean theorem to figure out what this question mark is equal to. I'll just call it A. All right, so by the Pythagorean theorem, okay, what I have is x squared plus a squared is equivalent to 1 squared, which is really just 1, right? Solving for a because that's what I want, so I can get the cosine right now. I see that a is equivalent to 1 minus x squared, and then to undo the squared, I would have had to take the square root. Sometimes when I teach this in person, students will ask, oh, why don't you have a plus or minus in front of the square root sign? Well, if you think about this expression a, it's meant to represent the length of a side of a triangle, so it wouldn't make sense to use a negative there because we can't have a negative length of a triangle side. Okay, so now that I have this piece of information here, what I can do is figure out what the cosine of theta is. So from my triangle, the cosine of theta is equivalent to adjacent over the hypotenuse, so that would be root of 1 minus x squared over 1, which is really just root of 1 minus x squared. All right, now notice this whole term down here really was the same thing as the cosine of theta. So what I can do is substitute that back in to get my derivative. So I'd have f, and I'll say by substitution. So I'm going to substitute that cosine theta back in. I have f prime of x is equivalent to 1 over, this is all the cosine of theta, which we found out was the same thing as 1 minus x squared. All right, so that was tedious to get to that point, but this is way nicer to work with. If we didn't do this right now, then what you'd have to do every single time you took a derivative involving side inverse is go through all of these steps or another proof. There's one other way to prove this, but it's not super easy either. So now I have a really nice clean derivative. With this, if I wanted to use it, I could simply pop values in for the x and get to some result. So, wait, I didn't write that in there. The overall conclusion here is that the derivative, so dx of the sine inverse of x is equivalent to 1 over root 1 minus x squared. All right, so it's a proof of it, why it's true. That's the overall equivalence. You can go through the same process for the cosine inverse, the tangent inverse, all of the inverse functions if you want to find the derivatives, but you can see that it's a lot of work. So like I said at the beginning of this, I will just give you the rest of the derivatives. So here's a table of all derivatives. These first 4 are what's going to be key for this course. You're not really going to have to use the secant or the cosecant inverses that much, but they're right here if you do end up needing it. I will not put those on exams, but they could be in your homework, especially if you do WebAssign. Okay, so now let's go ahead and look at this computationally. So you know what the derivative in general form looks like, but of course you want to be able to actually use it when you're doing calculations. So let's look at that. All right, so first computational example, we have y equals tangent inverse of 3x. All right, so to take this derivative, you're going to write y prime equals, you want to keep this form. So notice that you technically have a 1 multiplied by the tangent inverse of x. So you are going to have a 1 over, right? This requires the chain rule. So the outside of this function, the outside is the tangent inverse. The inside is that little 3x. All right, so for the tangent inverse part, and maybe I should do this in blue so you can see where it comes from. This is the outside. I have 1 over. I'm just maintaining this form I have right here. So 1 plus, now on this one I had an x on the inside and that translated to an x squared. Well, now I have a 3x on the inside, so that would be parentheses. Okay, I have to fill my parentheses back in, squared. All right, so this is the chain rule. With this, with the tangent inverse function, your little function goes in these parentheses to uphold the same form we have here. So I'm going to fill the inside of 3x back in. All right, so this is the derivative of the outside with the inside plugged back in. I still need to multiply by the derivative of the inside. So that's times the derivative of 3x, which is just 3. So this is the derivative of the inside. Right, and that is all going to be equivalent to, I'll just write this out, 3 over, so you might as well just multiply the 3 in the numerator there, and then I'll spell this out as 1 plus a 9x squared. And that would be my final answer. All right, let's try a couple more. All right, so this time I have the cosine inverse of 2x plus 1. So I need to recognize that again, I have the chain rule. All right, my outside function is this cosine inverse. My inside function is the 2x plus 1. Right here. Okay, so I have y prime is equivalent to, if I want to hold this form, I'm going to scroll back up here. Okay, look at my cosine inverse function. So for cosine inverse, I have -1. So I'm going to write a -1 up top over, have to hold the same form as the denominator. So I have a root 1 minus x squared, but now since I don't just have an x on the inside, I have to fill my inside back in. So I have root of 1 minus, this is where the inside piece comes in, so the inside squared, right? And I see my inside piece is the 2x plus 1, so that's what I'm going to fill in on the inside. All right, now I need to take the derivative of the inside, so when I take the derivative of 2x, I get 2. If I take the derivative of the plus 1, I get 0, so I don't need to worry about that. Therefore, I have that this whole thing is equivalent to 2 times -1 is -2 over root 1 minus 2x plus 1 all squared. If you wanted to, you could FOIL that out and simplify, but it's also not really necessary. All right, let's do one more. Right, this time I have x squared times the sine inverse of x to the third. All right, so notice when I read this, I have multiplication in here. I need to use the product rule. Let's spell out the product rule to start. So if I write the whole product rule out, I have y prime is equal to, the derivative of the first is x squared prime times the second is times sine inverse x to the third plus the first is x squared times the derivative of the second is sine inverse of x all cubed prime. All right, now I need to go through and take my derivatives. The first part of this is relatively gentle. The derivative of 2x squared is just 2x. I'll rewrite the sine inverse of x to the third plus rewrite the x squared. All right, so here is where we have, you know, our new work, our sine inverse work. So we need to take the derivative of this. Notice that sine inverse of x is inside of this cubic function. So that means the cubic function is our outside function. The sine inverse function is our inside function. Therefore, I need to take the derivative of the outside first. So the 3 will drop down. I have the parentheses that I'm going to have to fill back in, and that's raised to the second power. Right, now I need to multiply by the derivative of the inside. So this is kind of nice because I just have an x there, meaning I don't have to do anything fancy with changing what's on the inside. I just need to multiply by what we found the derivative of sine inverse x to be, and that was 1 over the square root of 1 minus x squared. All right, this isn't like this, but if I had like a 3x or a 4x or an x squared or something like that here, I would just need to plug that in where this x is. But luckily for this one, we don't have to worry about that. Okay, so I'm going to stop here with examples. This does give you the tools that you need. So the idea is now that you know these inverse functions and hopefully understand that if you have something inside of them, you just need to plug it into that portion where x is in the actual derivative. Everything else will combine with the chain rule and the product rule and the other rules that you've used. So essentially, you do have the tools that you need. The key is going to be figuring out how to use those tools to solve the question. So please try your homework, handouts, anything relative to this, and definitely ask questions if you have them.